In section 8.3, we'll talk about conditional probability, probability with intersection, and then independence of events. So we're going to start by motivating this with this following example. Consider the experiment of rolling a die. What is the probability of getting a 6? Just straight up. That is 1/6. All right. Now suppose you roll a die, and I look at it. And I tell you that yes, in fact, you did roll an even number. Do you still have a 1 in 6 chance of getting a 6? It's a 1/3 chance now, right? Because if you know it's an even, then how many even numbers could it have been? 3 of them. It could be the 2, the 4, or the 6. All right. So the probability of the roll as a 6 is now 1/3. Well, because essentially what happened is the following. You had 1, 2, 3, 4, 5, 6 for the sample space. And when I told you it was even, it just wiped out those. And so now you're dealing with a 1 out of 3 chance of getting a 6. When you have a situation where you are given little pieces of information like that, that is called conditional probability. All right. So the notation for conditional probability is the following. It's the probability of A given, and the symbol for given is a big vertical bar, B, where A and B are events that are part of the sample space. Okay. So this is the probability of A given that B has already occurred. The formula for A given B is it's the number of things that are in both A and B divided by the number of things. Actually, let's not say number of things. Let's say probability. Let's say probability. Make it formal. Probability of A intersect B over the probability of B. So in some sense, the B that you know has occurred becomes the new sample space. For example, up here, when we knew that the roll was even, we discarded the 1, 3, and the 6. I'm sorry, the 1, 3, and the 5. And now we're just looking at 2, 4, and 6. So how many of these is a 6? Just that one. How many total are there? There are 3. So it's 2, 4, and 6. All right, so this is the formula you're going to need right here. Part 2 wants us to write it out with all the notation. So A is the event of getting a 6. B is the event of getting an even roll. So the probability of getting a 6 given that we have an even roll, that is the probability of A given B which would be the probability of A intersect B divided by the probability of B, now you have to check the intersection. Sometimes the event that you're looking for is sometimes not completely the same event that you end up with, because you know that something has already happened, right? We'll get into some of that later. In this case, it doesn't matter. So A intersect B, the probability of that is 1 out of 6. And then the probability of B, so B was the event of getting an even roll. That's 1/2. And then to work with fractions, you multiply by the reciprocal, so that's 1/3. Now, if you can see the counting, then go ahead and do that. You're welcome to do that as well. Questions?
I'm a little bit confused as to why you put 4 and 6, because isn't that just A, but in the formula it's A intersect B?
So what are all the simple events of A intersect B? So which dice rolls would be a 6 and even?
6, 4. Oh, no, just 6. Okay.
Just the 6. Okay. Just the 6. Because A says it has to be a 6. B says it has to be an even one. So with the A, you get the 6. With the B, it's 2, 4, and 6. But the only one that's in both is just the 6. So it's 1 out of 6. And then the probability of B is 1/2, because that's 2, 4, and 6. Yeah, as opposed to 1, 3, and 5. All right. Example 3. Consider the wheel below. The probability of landing in each sector is given in the table. So you see how the wheel is not evenly spaced. So the equal likely assumption does not apply here. There's the different sector sizes give us a different probability. But it's a quarter probability that you'll land in a 1, 0.2, 0.2, 0.1, and then 0.25. What is the probability of getting a 2 given that you have spun an even number? All right. So here A is a 2 and B is even. So we want the probability of A given B. That would be the probability of A intersect B over the probability of B. Event A is 2, event B is even, so their intersection is just the probability of getting a 2. It's just the 2. What is the probability of getting a 2? That is 0.2 from right here. And then what is the probability of getting an even? Yeah, that's 0.3. So this one and that one. They're disjoint events, so you add them. So it's 0.2, and you want me to write that out, that it's 0.2 and 0.1 added together? And what's 0.2 divided by 0.3? You can either do a decimal or you can do a fraction, either one. 2/3. But let's stop and make sure this is making conceptual sense to you. Okay, because most of you look confused at this point. And there's not much I can do about it. I'm here to answer questions if you need them. Okay? But here it is. There's a 4 and there's a 2. You spin the wheel. You were told that it's an even number. Knowing that it's an even number, what are the percentages? What are the probabilities of getting the 2 versus getting the 4? The sector that is a 2 is twice as large as the sector of a 4. So it's 2 to 3. 2/3 chance. Go ahead and try. Let's see, B and C and D and E. Go ahead and try those and see what you can get. Part C says, what is the probability of getting a 1 given that you've spun a number less than 4? So A would be a 1 and B would be 1, 2, and 3. So the probability of A given B is the probability of A intersect B over the probability of B. So A intersect B is still just 1. And what's the probability of 1? 0.25. And then the probability of B is 1, 2, and 3. So what was that? That was 0.25 plus 0.2 plus 0.2? 0.65. And then this one is, that's the one I did a while ago. Yeah. 0.385, let's say. D, what is the probability of getting an even number given that you have spun a number greater than 2? So written as a set, an even number here would be 2 or 4. B, given that you've spun a number greater than 2. So greater than 2 would be 3, 4, and 5. So the probability of A given B is the probability of A intersect B over the probability of B. Now, notice that A originally had 2 and 4 in it, but the 2 is out because I know that I've spun a number greater than 2. So A intersect B is just which number? It's just the 4. What's the probability of 4? 0.1. And then the probability of 3, 4, or 5? Is 0.55. Okay. And that's 0.182. All right, so does everyone understand why I had to take the 2 out? And I didn't get to consider the 2. It's not in the intersection. What is the probability of getting a 3 given that you've spun an even number? So A is 3, B is 2 or 4 because it's an even number. So the probability of A given B is equal to the probability of A intersect B over the probability of B. What is in A intersect B? Nothing. The probability of nothing is 0 over whatever this probability is. It's 0. In other words, what's the probability of getting a 3 if you know I did an even number? 0. Can't happen. Because the number's even, you know that it's not going to be a 3. All right, questions? All right. Here are some things that you can do to sort of help yourself out when studying for this class. You need to be doing the homework. You need to be doing it to the point of understanding. Okay? I believe that some people are doing it to the point of completion, which is good. But if you're using all the helps all the time, every time, that is not going to be sufficient. Okay? Use the helps appropriately. All right? But then you need to make sure that you can do those problems even without help. Okay? That's how you get good and do things on the be able to do problems without help. Slack is available. All right? The Math Lab is available. The Math Lab is around the corner and around that other corner. You can go in there. They have computers in there. You can log on. You can do your homework while there's people there that can help you and assist you with doing it. The number one thing that you can do to help yourself is form a study group. Okay? Because the summer is fast-paced, I would think that your study group probably needs to meet every day to work on problems and things like that. Go over the notes. Rewrite the notes if necessary. Make sure you're bringing the notes to class. Is it a problem for you that the notes aren't being posted until 10 o'clock? Is that a problem? Because what we can do, we can go back to the old notes. But what I'm doing is I'm revising the notes as we go. Okay, but if it's a problem, I'll just ship off all the notes that we have, and you can just print them all, and we'll just use the old notes for the rest of the semester. I think that's what we'll do. Okay. So they'll look ugly, but that's all right. Okay. So we'll make that available. But you need to print them and bring them to class so that we can use them. Okay. You need to be reading the textbook. The textbook has examples and more examples. When you're on the ebook online, you can look at an example and then you click the video to see someone else work that problem. In many cases, it's the author of the textbook, so they're the experts on all this stuff. You can see them working all this stuff. Okay. Any other questions? Any other suggestions I can give to you? I know it's intense. I know it's something, but we got to try to get through this. Okay. Looks like we already lost a couple of people from exam one. Okay. All right. When I call your name, come pick up your exam. Like I said earlier, if it's not good a grade that you wanted or were hoping for, keep working at it. Come see me during office hours. Form that study group. Okay. Go over your test because, like we said earlier, your final is comprehensive, so it covers all this stuff. Okay. Rosalind? All right. Have a nice day. I'll put the homework up when I get back to the office. Yeah. There's nothing on right now, so I'll put it up when I get back. Griffin? Alexandra? Brett? I've got a key over here. Yeah, you want some with it?
No, I didn't have what I wanted.
Aiden? Nia? Courtney? Colin? Samuel? Sam? Adam? Rainbow? Grant? Yeah, I've got the keys. Go and see it after. Brenda? Mike Keys? Ben, brother? Patrick? Frank? No, Kyle? No. Kyle's not here today. All right, anyone have any questions? You need to choose a manager, then choose a manager. Choose and choose. Yeah, because n minus 1 factorial is the rest of n factorial. Okay.
thought I said the next grade.
This one needs to multiply out.
Almost. You should be adding, but it's not choosing. It's power, just like
So it's, yeah,
24, 26 to the 4th, 26 to the 5th,
okay,
26 to the 6th.
What's wrong? What does that say?
That should be not P or not Q.
So it's this one?
Yeah.
So the sign flips?
And what you need to do is do a table to see that. Truth table.
How does it change? Why does it go from 4 to 9?
It's like this one. It's the same thing as with. There's actually a rule for that. It's called the Norton's law. But it's like it's a set like this, right?
Yeah.
Okay. Then we could have A intersect B common, and that's everything except for this, right? Everything outside here. Right? Now, what if I had A complement union B complement? That would be everything outside of A, which is all of this, right? Including this little portion of B. And that is everything except for B, including some pieces of A. And because it's union, it's just anything that has any sort of shape. So the only thing that was avoided was this. So these things are the same. So that is a general rule with sets and with propositions. So if you had the negation of P and Q, that is not P or not Q. If you had P or Q, the negation of that is not P and not Q. And then you have the set version of that as well. So A intersect B complement is the same thing as A complement union B complement. And if you have A union B complement, that's A complement intersect B complement. So when doing unions and intersections, ands and ors here, disjunction and conjunction, the complementation does flip.
Unions and
Union is a word.
union is over.
Intersect. Because it looks like an A.
Yeah.
We're choosing a manager first.
Yeah, choose your manager first.
So then
So on A, the man is a manager. How many men do you have to choose from? And I'm here to choose. Managers of it.
this one's 37 left.
Right. Well, you got that part though.
Yeah.
You got that part. You just need to multiply this by 8 choose one.
Okay.
Because you have to choose it. Then, let's see. Then on part B,
So multiply this, so you choose one to the final answer.
yeah, the 14 choose 3. Yeah, it should be 8 choose 1 times 14 choose 3. Okay. And then on B, the man is a manager, and then it's 3 women. So you chose 3 women, right? Now you have to choose the manager again. So that's 8 choose 1. And then the partner is all women. Now, you still have to choose manager because it's different to be a manager than it is to be a worker. So how many women do you have to choose from? How many managers are you choosing? 1. Then you have to choose the 3 workers. So how many women do you have to choose from now? 6, because one of them is a manager. 6 chooses 7. Very good. Okay. For probability of A not equal to 0 and probability of B not equal to 0, we have the following. The probability of A given B is equal to the probability of A intersect B divided by the probability of B. And this is our standard formula for conditional probability from yesterday. Equivalently, I could also write the following. The probability of B given A. This would be the probability of B intersect A, but A intersect B is the same as B intersect A. It's still just two sets being intersected. So I'm going to write that as A intersect B. What changes in the second equation? This is set A. But notice what both of these equations have. They both have the probability of the intersection. This gives us two different formulas to find the probability of intersection. The probability of A intersect B is equal to either this first piece, where these have been cross-multiplied. So it's the probability of A given B times the probability of B. Or, from the second equation, it's the probability of B given A times the probability of A. And of course, the order that I multiply these in is not relevant. So this left one could be probability of B times the probability of A given B. And the one on the right is probability of A times the probability, probability of B given A. In some sense, you can think of the given symbol as sort of a denominator, where here's the probability of B, and it's on top, and so now you need the B part on the bottom. Sort of cascades down and through. Let me show you how to use the intersection formulas. A wheel has a 40% chance of landing on a red square. There are 3 equal red squares on the wheel with the numbers 1, 2, and 3. What is the probability of landing on a red 2 square? All right. I'm sorry? Square, space, whatever. Yeah, sector, could be that. So here's your wheel. And we don't know much about this wheel. We only know a few things, but we know enough. We know that we have a 40% chance of landing on a red space. Let's say space. So 40%, 50 is half, so let's say, does everybody buy that that's 40%? Let's say that that's 40%. Now, inside this 40% sector, there are 3 equal spaces with a 1, a 2, and a 3. We're going to use that information to find the probability of landing in the one that is red and 2. So this middle one right here. All right. So let's let R be the event of getting the red space. And let's let T be the event of getting a 2. Now what we don't know is if there are other 2s on the wheel. That may be a blue 2 or a green 2, something like that. We don't know any of this. So we have to go at it from a different way. We are looking for red 2. So that would be red and 2. So that's the probability of red intersect 2. Using my intersection formula, I'm going to rewrite this as the probability of red times the probability of 2 given red. Do you know what the probability of red is? 40%. As a decimal, that's 0.4. Now, knowing that you have landed on a red space, what is the probability of landing on the 2? Well, how many spaces are there in the red spaces alone? So this piece right here says look only within the reds.
1, 2, and 3.
The sample space within the reds is 1, 2, and 3. Those are equally spaced sectors. So in the red alone, what's the probability of landing on the 2? No? No? This piece right here says you are in the red, period. So you ignore this piece of the wheel. So now this is the only part of the wheel you can consider. What's the probability of landing on a 2 if you can only look at this part? 1/3. Yeah, 1/3. Okay. These are 3 equal spaces. So knowing that you're in this red part alone, you ignore the rest of this, and this is 1/3, 1/3, 1/3. So the landing on the 2 is 1/3. What you're doing is okay, but what you're doing is too much. You were still thinking about the 0.40, the 40%. You're trying to do the whole thing. You can't do the whole thing with these problems. You got to break it down and do little bitty pieces. Otherwise, it's going to get too complicated. So this was 1/3, and together, 0.4 times 1/3 is 0.133, or you could write that as a fraction 11 out of 30.
0.133, I got 215. When I just put in the calculator.
2 out of 15?
Yeah.
Okay. Let me check that. Yeah, that's right. That's right. Yeah.
That's what my calculator.
Yeah, 2 out of 15. Yeah. Now, what's the obvious question you should have for me at this point? How many formulas do you have for intersection? Yeah. So the question is, could you have used the other formula? Yeah. So could we have used the other formula to do the intersection? Let me write that in green for us, because the answer is no. But could it have been this? the probability of 2 times the probability of red given 2. Why can you not use this formula?
Because you don't have to.
Even if it's 2, it may not be the red 2, and you have to go by red first. It has to be a red 2.
Eventually you want to get to the red 2. If you knew these pieces of information, this would still give you this answer. The question is, do you know these two pieces of information? What about this? The probability of a 2. You don't know that answer. Because you don't know what the rest of the wheel looks like. You don't know if this is a 2, and this is a 2, and this is a 2, and this is a 2. You don't know any of the rest of this stuff. So you don't know the probability of 2 to begin with. In some sense, you're going to have to think about this as going down a path where you have a piece of information and you have some more pieces of information. And that leads me to our next topic, which is probability trees. Any last questions over the wheel? Okay. So the probability tree is a way of organizing the information. And it's very similar to the trees that we've done in the past with the shirts and the pants, or the ice cream and the peanuts and the bowls, where you just keep making trees and going forward. We're going to use that with given probability today. Example 5. 2 balls are drawn in succession without replacement from a box containing 3 red and 2 green balls. What is the probability of drawing a green ball on the second draw? All right. So the tree looks like this. You have a starting point. And you're going to draw 1 ball from the box. What are your 2 choices for the balls? Red or green. So here's red, and here's green. What is the probability that you draw a red ball on the first draw? 3/5. There are 3 red balls in the box and 2 green balls, so that's 3 out of 5. So you put the probability on the tree itself. So it's 3/5. What is the probability of drawing a green ball? 2/5. Now this was the first draw. It is important to note that this drawing is done without replacement. So once a ball comes out, you no longer consider that colored ball. On the second draw, you still have 2 choices, red or green. And it doesn't matter if you had a red one or a green one to start with. You still have red and green in the box. We need to figure out what the probability of getting a red on the second draw is. The key here is the following. You want to know the probability of getting a red ball with the second draw, given that you drew a red ball on the first draw. See, knowing what color ball came out on the first draw affects the probabilities going forward. So this is conditional probability.
The question says green ball.
That's right. We're going to fill out the whole chart.
Okay.
Yeah, we're going to fill out the whole chart. And so where would I be interested in to find the probability of drawing a green ball on the second draw? Where would that be? Here? No. Here? Yes. Here? No. Here? Yes. So the sum of this one and this one will be the solution. That's very good. Yeah. All right. So we've drawn a red ball. We're going to draw a second red ball. How many red balls are left in the box? 2. How many total balls were left in the box? 4. I encourage you to leave these unsimplified on the tree. That is fine, because it's going to make the adding and multiplying easier going forward. Given that you drew a red ball on the first draw, what is the probability of getting a green ball? So how many green balls are in the box? 2. How many total balls? 4. Given that you drew a green ball on the first draw, what's the probability of getting a red ball for the second draw? So how many red balls are left in the box? 3. How many total balls? 4. Given that the first draw was green, what's the probability that the second draw is green? How many green balls are left in the box? 1. And total number of balls? 4. Notice at each branching, the sum of the probabilities is what? It is 1, right? 1 and 1 right there. So the branching has to branch out into all possibilities, right? You have to cover every possible outcome. Now, I'm going to relabel these as R1, R2, G2, G1, R2, and G2. We are looking for the probability of G2, a green ball on the second draw. As we mentioned, there are 2 ways to get there. Those 2 ways are to go through having a red ball on the first one and then a green ball on the second one, or a green ball on the first one and a green ball on the second one. So this is probability of R1 intersect G2 plus the probability of G1 intersect G2. Those are the 2 ways to get to the green ball on the second draw. Let's expand the probability of R1 intersect G2 using the previous formula. This would be the probability of R1 times the probability of green 2 given that the first ball was R1. So it's the probability of getting a red one on the first draw times the probability that you get a green one on the second draw, knowing that you had a red one on the first draw. That's the first part. What's the second part? It's the probability of what? G1 times what? G2 given G1. Does everyone see where all this is coming from? You don't see it? Okay. You have to go back to the previous page to look for, well, first let me ask this. Do you understand why I split up the probability of G2 into these 2 parts? Okay. What are the 2 ways of getting to G2, to a green ball in the second? You either had what? You either had a red one on the first draw, or you had a green one. Okay. But you have to follow. It's red and a green, or green and green. So it's intersection. It's red and green, or green and green. That's the only 2 ways to get a green at the end. So that's why we use intersection. Then from the previous page, we're going to use our conditional probability that we created the formula for. The probability of red intersect green, R1 intersect R2. It's the probability that the first ball was red times the probability that the second ball is green, given that the first ball was red. So you're going down the path from here to here to here through this first part. So let me go ahead and finish the problem. The probability of a red 1 is 3/5. What is the probability that the second ball is green, given that the first ball was red? It is 2/4. So you go down the path where you are given that the first ball was red. And then how do you get to second ball being green? Green 2? It's 2/4. That's this piece and this piece. Plus, what is the probability of green 1? The probability of getting to here is 2/5. And what is the probability of getting to green 2 from green 1? 1/4. Add these together. 6/20 plus 2/20 is 8/20, which simplifies to 2/5.
Why do you leave? Oh wait, never mind.
No, ask it. Ask it. I think it's a good question. If it's the question I'm thinking of.
I was looking at it, and it looked like you were leaving the number of balls the same, but I think I read it wrong. Or did I read it right? Are you leaving them the same?
No.
No. Okay, so I read it wrong.
So the number of balls that are in the box.
They were, because I read without replacement, but I just had it wrong.
So here let's go down this path. So how many green balls are in the box to start with? 2. How many total balls are in the box to start with?
Oh, 5.
5,
Yeah.
right? Because there's 3 red and 2 green. So that's 5. And now this is 1/4, because when you were here, you take out one of the green balls. So you started with 2, then you're down to 1 green ball. But when you took out the green ball, you took out 1 ball from the box itself. So there are only 4 balls left in the box. Right.
Now, the order of the third one that you have there, 1, 2, 3 divided by 5, 2 divided by 4.
Here and here. Here to here.
Right?
Mm-hmm.
Okay. That's what I'm trying to get at. This order here. The 2G1, the G2, G1, you give this one being G1 and this one being G2. I'm going down like this.
Mm-hmm. No. This one is this one. So the probability of G1 is 2/5. These 2 are the first 2. And then these 2. We just don't have enough space on the screen to show.
Got it. Yeah.
Yeah. That's all I'm saying.
That clears it.
That clears it up? Okay.
A lot.
Yeah, see, this is equal, and then this is plus, so you just think of this as one big line.
All right. Thank you.
What's interesting to note here is this. When you do such a multiplication, and you have R1 and R1, I told you it's sort of like it cancels, right? If you sort of pretend like this cancels, what are you left with in this first piece? G2. Hey, that's what you want. G2, right? And if this sort of cancels, what are you left with? G2. So you're adding up the different probabilities based on the different ways of getting to G2. There are 2 ways to get to G2. You either go through a red ball or you go through a green ball. Now, in your homework, you'll do some problems where they say you do replace it, right? So the probability of G1 with replacement is 2/5. And then given G1 with replacement, what's the probability of another G2? It's still 2/5. Yeah. So the probability doesn't change if you're doing replacement. All right, questions over the tree. Okay, go ahead and work with your partner on example 6. You're going to build the tree, and your event is flipping a coin. Now, this coin is not fair, so the weights for heads and tails are different. You'll need to, you know that the weight and the probability for heads, you'll need to, with your partner, come up with the probability for tails, and then ultimately, you're going to flip it twice, which means you're going to come out with a tree, 2 branches. All right, go ahead and work with your partner. And what is this and what is that? Okay, one? Yeah. Use the subscript to denote which flip you're on. In this case, yes. Yeah, you can use decimals on this one. Well, you don't lose anything. You lost ball. Yeah. You don't lose anything. So the probability is twice.
You just do heads and tails. And then it asks the probability of getting the same outcome on both flips. So it'd be 2 heads. So the 2 heads would be 0.666, and the 2 tails would be 0.1.4. You multiply these 2, and then you multiply these 2. There you go. That's what I got from this chart. Yeah, like how I did this one is how I did this one.
Let's put the mark on
Is that
R1 should be
or times H2?
and H2. And my probability.
Yeah, they're both 0.6 because that's the probability of landing on head. So you just multiply them together. Because it gave you 0.6 up there.
So that was not the probability of 0.6, and then if you make another branch.
Yeah. And I feel like it's still 0.6, but if
And we were only doing it twice.
yeah, so this is the first flip, right? Like you can land on heads or tails the first flip, and then the second flip is heads or tails.
But it wouldn't. 0.6 would be changed.
I don't know, because this one changed, but that's because you're taking something out. You're keeping the same point, so it shouldn't change at all. I think it shouldn't change.
So this would be 0.46.
Yeah.
This would be 0.6.
Because you'll always have a, like, heads or tails will always be your two options.
Right. Okay, so you're not taking it anyway.
Yeah.
So you still want this, and you still want even though it's not the one that's in the desired part. So part of the question is just going to say draw the tree, and then use the tree to find stuff. Because you have tails, and then you have.
And then how do I put this into the
So what events constitute outcomes are the same? Or is that, that's what it is. Yeah, same outcome. So what events would that be? No, you're going to flip it twice. So if they're the same, what's the flipping look like? It's heads. So that's the probability. Yeah. So you multiply through the table to get the end result. You multiply, right?
Yeah.
Multiply this way. Multiply that way. Is that right? That's it. You got it. Oh, so that's an example. Yeah. Is if heads is more likely. So, is it, when you work it twice, is it more likely or less likely that you will flip two are the same? Or so, and the answer is more likely the same.
Confusing with this one. If you just read the traits of the easy, all the formula and R1, R2, everything. Because I was staring at the board for like 5 minutes, just like, I need to keep
Oh, yeah. That sounds right.
The point doesn't change whenever you put the right? So this is sort of like a
Basically,
okay. And then all right, let's check it. If we were to draw the tree, it would look something like this. So heads 1, tails 1. The probability of heads is 0.6. The probability of tails is 0.4. Then the second flip, we would have heads 2, tails 2. Now the coin does not change, so the probabilities stay the same. This is 0.6. This is 0.4. And 0.6 and 0.4. Now the outcome you're looking for is the same outcomes. So it's head, head, or tail, tail. If you're doing this technically, this is definitely what you would write. The first question is, the outcome of heads, heads, is that disjoint from tails, tails? The answer is yes. So you would take the two probabilities and add them without worrying about the overlap. Then the probability of heads, heads would be the probability of heads, 1, times the probability of heads 2 given heads 1. Plus, and now for the tails, tails, it's the probability of tails 1 times the probability of tails 2 given tails 1. And then you read these numbers off the tree. So heads 1 is 0.6. Heads 2 given heads 1 is 0.6. Tails 1 is 0.4. And then tails 2 given tails 1 is also 0.4. Now I'm going to mark these so you can see where each of these came from. Number 1, number 2, number 3, and number 4. This was the number 1. This was the number 2. So they are different 0.6s because they come from different places in the tree. Number 3 and number 4. 0.6 times 0.6 is 0.36. 0.4 times 0.4 is 0.16. And you add them together to get 0.52. Alexandra.
I got everything right starting from when we go to, I guess, the third line.
Mm-hmm.
And I don't get for the very first line you wrote why we have to put that in there.
This one?
Yes.
We're just talking about the outcomes that we want.
So, but you won't count it wrong.
No. In fact, when you do this on a test, this is where I want you to start.
Okay.
Here and below.
Okay.
Because what I want you to be able to do is to draw the tree and do this calculation.
Okay. So
Okay.
you won't count it wrong.
No.
I guess in my head I did those parts.
No.
It's just my head. Not on.
The other thing to do here is the following, and maybe this will make more sense. The other thing to do is declare an event. So the sample space of flipping the coin twice has 4 things in it. Heads, heads. Heads, tails. Tails, heads. And tails, tails. And then which events does this question ask for? Yeah, heads, heads, and tails, tails. And then maybe you just say probability of E.
Okay.
We are doing all of this work now so that you understand where it is all coming from. That is the goal. Practically, this is what you do. And speaking of the practicality, here is what you do. You isolate the leaves of the tree, the ends of the tree. You want this one because that is heads, heads, and you want this one because it is tails, tails. And then you just follow the tree through those probabilities and add them up. That is what I'll expect you to do on the test. Okay? So it would be 0.6 times 0.6, 0.4 times 0.4, and then you add those results up. What you have to be careful about is picking the right endpoints to add up. Question? All right. So you'll see some problems like that on your homework. Let's talk about independence. So we say that 2 events are independent if their outcomes do not rely on each other. Okay? So basically what happens is if the two events that we consider, and the events are either dependent or independent. We consider these two events, and if they influence each other, then they are dependent on each other. If one has no bearing on the other, they are independent. So basically it comes from the following. If you look at the probability of A intersect B, this should be the probability of A times the probability of B given A. All right. Two events are independent if when you go to compute the probability of B given A, knowing that A has occurred doesn't change anything. So, for example, let's say I deal a card, and I look at the card, and it's a heart. How does that affect the probability of this card being an ace? Does the fact that you know that this card is a heart tell you anything more about this being an ace or not? The answer is no. Just because I've told you that this is a heart, the probability that it is still an ace is completely the same. That's independence. Yeah.
So, for example, example 6 that we just did, that would be independent. But the one before that with the balls, that's dependent because it's based on like which ball was taken.
You got it. And in fact, the example you cite is actually example 7.
Okay.
Yeah. But let's write the formula. So since given the probability of B given A doesn't, if they are independent, it does not influence B, then the probability of A intersect B is the probability of A times the probability of B, period, without the given A part. And you will see this as sometimes written as test for independence. If they ask you to test for independence, then you just work both sides of the equation and show that they're equal. If they are equal, they're independent. If they are not equal, they're dependent. Other problems that you will see will say events A and B are independent. Calculate some of the following. If they are independent, then you know that this equation is true and you can use it for whatever you need it for. Let's look at example 7. Example 7 says, suppose you have a fair coin, so we're back to 50-50 here. Show that the events heads on the first toss and heads on the second toss are independent. So I'm going to create two events. We're flipping the coin twice. What events, or simple events, go into A that represent heads on the first toss? So what could it be? Heads, heads, or heads, tails. Yeah. So A is strictly heads on the first toss, heads and heads, and then anything else that could occur. What would be event B, the event of getting heads on the second toss? Heads, heads, and tail head. Yeah, tail head. So you want heads on the second toss on this one. Now the question is, do you believe that these two events are independent? In other words, the mere fact that you got a heads on the first toss, does that have any influence on you getting heads on the second toss? The answer is no. In some circles, they say that the coin has no memory, meaning that if you flip it now and it comes up with heads, it doesn't know that it came up heads when you flip it again. It doesn't know. Because every time you flip a coin, it's a 50-50 chance that it's going to be heads or tails. That's like they say, we dealt with this problem the other day. We flip the coin 19 times in a row, and we get all heads. Heads, 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 all heads. Do you believe that it is more likely to get tails on the 20th flip because you got 19 heads in a row? And the answer is, if it's a fair coin, the answer is no. It doesn't know that it flipped it 19 times and got heads. It's still 50-50 that you're going to get heads or tails on the next one. Let's continue here and show that these are independent. So what is the probability of A? There are two things in A. The sample space was the four things: heads, 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 tails, tails, heads, and tails, tails. So the probability of A is 1/2. Probability B is also 1/2. Let's look at the set A intersect B. What is the actual set A intersect B? It is heads, heads. There it is, and there it is. Oh, heads, heads. So the probability of A intersect B is what? It is 1/4. What is the probability of A times the probability of B? The probability of A is 1/2. The probability of B is 1/2. And 1/2 times 1/2 is 1/4. So since the probability of A intersect B is equal to the probability of A times the probability of B, they're independent. So you write A and B are independent. Questions? All right, go ahead and work with your partner on example 8. You are testing for independence. So you need to determine whether or not these events do, in fact, turn out to be independent. So we're going to do probability. What's the probability? There are 13 days. I'm going to call it probability. If they are what is E?
I don't like. I get it. I don't want to write it. Yeah.
Because these two are not equal, so that would be
one out here.
just because you know it's spade doesn't mean that you know it's a spade card. So that will make it that could be if it's a club, it can't be a heart. So that's independent of each other.
We're not finding the functionality of how are we working with the right now?
We're just trying to get it independent. Pretty sure.
Like you see how these two are equal, and then it's independent. These two are 1352 and 1352, so these are equal, and that to me is not independent. Because of 1352 and 1352. 13 is like this is the and or whatever it is, or I said an A or, so the spade, right, is 13. And the base card is 4. So 13 and 4 are not equal. Yeah, 3. Oh, there's 3 bases. 3, 2.
So, well,
Well, I think the only way to do it is to show, I showed that
What is the event?
1352 and 352 are not equal.
13 are 2 what?
352 is okay, but they're still not equal. But I just can't count.
So that's all you do is
Just show that they're not equal. That's what I got from what he was saying.
So the tricks: Jack spade, king spade, king spade. Right.
the card drawn is a club, so there's 13.
You got to show the work as well. Right? So you figured out the probability of E. Figured out what the probability of
So B's already.
That's right. So you do this. You have done. You do that by itself.
That makes sense to me.
You state the probability of E intersect F is equal to some number by itself. Erase all this. Erase all that. Except for the now, usually you know, based on our conversation, the probability of E intersect F is 3 out of 3. Because now we're going to
Well, you're not really trying to find the probability of this, you're trying to figure out the
probability.
So all it is would be 13 times 12. 13.
What is the
Now, do you know that that's okay. That's the kind of thing you do. Probability. They are in the
Well, I think
you would come up with a probability of you spin product of everything that is decent, not
Start really small.
Then you need to do probability of intersection.
They're equal to each other.
If you do that simple,
Yes.
So that's what we did in example 7, and that's
I don't understand.
So I got 3 different
based on consideration, other than knowing your probability, you do that. And now, this problem, you equal to that number.
They really don't have to be math.
That's what that E is.
Yeah. So what's the problem?
Well, that's what we're trying to say, is are they in the relation of each other? So you can now, so if I go on card, and I do a mistake,
But wouldn't it be
with the probability about whether or not this card happens to be fixed or
Oh, it has to be looked at.
It's still in the same proportion of the
Or wouldn't it like reduce it from 50 to
Okay, and the second one. That's it. I mean, if you read it, that would make sense, but math doesn't always make sense the way you read it.
this is probability.
But so the B is B. Because they can't be both.
Yeah, but that would make them independent of each other, right? Like, if you have a club, then you can't have cards. They're dependent. They're independent. Like, you can't have both. That
that one on top, if you have a spade, you can't have a face card because they're dependent on each other. Is how I would understand. It's like, yeah, like when you're saying out loud, that would make sense, and then that would totally mathematically would obviously check out.
Cards are both spades and
So, but I'm sure his way is the right way because it was more complicated. You gotta think about it.
If it was a
So, because you've shown that this one is a dual product, they are in.
And then this one is
Be sure to do the second one.
because as a heart, if you have a heart club, there's going to be 0 in your A and B. And then 1352
Well, we got to say two.
times 1352 does not equal 0. So that would make
Not
this
saying either one here.
like out
That
loud.
one should not have. Something. Just use the regular word. So what's the probability? What's the probability that?
This one is for physics.
Okay. What's the probability?
They equal to each other.
That's alright.
Now, if you're the figure all this stuff out, this was like 1352, this was 1352.
Once you multiply so there's a possible for
You said this. Because
13 over 52. First one, and then the card draw gets a fire.
so there's a probability of 0. B would be D.
Right.
All right, let's check them. Yes, let's check them. Example 8, Part A. Determine if the being a spade and being a face card are independent or dependent. So the probability of E, the probability of getting a spade is 1 out of 4. There are 4 suits. Each suit is equally likely, so it's 1 out of 4. You could also put 13 out of 52. Face card. There are 12 face cards in the deck out of 52. And then you need to consider the intersection. The intersection of spade and face card is the set of cards that are both face cards and spades. That's the king of spades, queen of spades, and the jack of spades. So there are 3, and that's out of 52. So if this is in fact equal to the probability of E times the probability of F, then they are independent. And if you work this on the calculator, sure enough, it's 3 over 52, so they are independent. In part B, we have E is the card drawn is a club, and F is the event that the card drawn is a heart. What is the probability of E? 1/4. What is the probability of F? 1/4. What is the probability of E and F? That is 0. You cannot be a club and a heart at the same time. So, are these independent or dependent? They are dependent. So that's 1 over 16, which is not equal to 0. So they are dependent. Now think about what that means. If I draw a card from a standard deck of 52 cards, and I say, it's a heart, what's the probability that it's a club? 0, because it's a heart. It's not a club. you.